Okay, so good evening and welcome back to this problem solving session for the NPTEL course Foundation Engineering. So, in the last week, we started discussing on this heat pile wall. So, how to determine the net earth pressure distribution for a cantilever sheet pile wall and how to determine the associated embedment depth by imposing some margin of safety. Now, in this week, we proceeded further and we have seen how to determine the same, that is the net earth pressure distribution for an anchored sheet pile wall. Okay, so before that we have seen that this sheet pile wall may be of two types. The first one is a cantilever sheet pile wall and the next one is anchored sheet pile wall. So a schematic diagram of the anchored sheet pile wall is presented in this slide. So this is the anchored sheet pile wall and this is the anchor. Okay, so by which this uh, wall is basically anchored to the ground. Now to determine the embedment depth of this sheet pile wall, so we have used the free earth method. So there are two methods available to determine the distribution and the embedment depth of an anchored sheet pile wall, and those are free earth and fixed earth method. So for this time being, as far as the scope of this course is concerned, so we have seen the implementation of free earth method or the utilization of free earth method in determining the net earth pressure distribution on an anchored sheet pile wall and the determination of its embedment depth. Okay. Now coming to the next part of this week, we have also learned about breast excavation. What are the different components of a breast excavation? So this is the schematic for an breast excavation. So these are the two sheet pile walls. These are called struts. Okay. So these are the Euler beam or valley. So I hope by this time you know all these terminologies which are involved for a breast excavation. Now the main objective in this kind of problem as a geotechnical engineer is to determine the axial force in the strut, to determine the maximum movement in the wall and the Euler beam or called valley. Okay, that we'll see through some numerical example problems in this session. And lastly, we have learned about the underground conduits. So what are the different uses of underground conduits, like its application in the drains, wells, gas lines, water mains, culverts, tunnels, and so on. Then different types of underground conduits. So it can be ditch conduit, positive projecting conduit, negative projecting, and imperfect ditch conduits. Okay. So these are the four type of conduits which we have learned from this specific course. And lastly, we have learned about the theory of soil arching given by Marston's load theory. And this soil arching can be of two types, active and passive arching. So these are the pressure distribution corresponding to, this is corresponding to active soil arching and this is corresponding to passive soil arching. So we'll see what is the mechanism of soil arching and how this active and passive the soil arching is categorized into two different terminologies like active and passive. And at the last, we have also seen about the derivation of stress transfer and its application through an example problem like tunnel through sand. Okay. So now we'll start our today's session by taking this problem, problem 1. So where a cantilever sheet pile in a pure clay soil is shown in the below figure, and we have to determine the net earth pressure diagram on the sheet pile. So this is similar to this is not similar to this is obviously a cantilever sheet pile wall, since we are not having any anchor by which this wall is basically anchored to the soil mass. retained soil mass. So obviously this falls under the category of cantilever sheet pile wall. Now in the last week we had solved a cantilever sheet pile wall, but for the questionless soil deposit. So in this case, we'll see the application of cantilever sheet pile wall for a purely clay deposit. Now this is the water table location. Okay. Before that, this is the height of the cantilever sheet pile wall. That is, it's having a total height of 4 plus 2 6 meter. This is the dredge level, and this is the embedment depth of the wall, and this is the water table location. So water table is basically located at a depth of 4 meter from the ground level. And question that is having a value of 35 kPa, saturated unit weight 17.5 kilonewton per meter cube above the groundwater table, and below the groundwater table submerged unit weight is given as 7.5 kilonewton per meter cube. Okay. So as you know that depending on the deflected pattern of this wall, we can divide the entire soil mass zone into 4 regions. Okay. So this is the dredge level, and this is, we are assuming, the point of rotation for this wall. Now, after deflection or after displacement, the deflected pattern of the wall will look like this. Now, depending on this deflected pattern, this entire soil mass region can be divided into 4 parts. So this is region 1, this is region 2, this is region 3, and this is region 4. Now out of these 4 regions, we have also identified in the last class that region 1 and region 3 will be under active state, and region 2 and 4 will be under passive state. And this is from the basic fundamentals. Why? Because in region 1, the retaining wall is basically moving away from the backfill, and region 3 also. So therefore region 1 and region 3 will be under active state, whereas for region 2 and region 4, the wall is basically moving towards the backfill. Therefore these 2 regions will be under passive state. Now this, considering these active and passive conditions, we can easily draw the individual earth pressure distribution which are basically associated with this region. Now depending on that region, we can easily draw the net earth pressure diagram. Now we can conclude from this deflected shape of the wall that up to this dredge level, so this is your dredge level, so up to the dredge level, or rather we can say above the dredge level, in region 1, whatever may be the earth pressure, obviously under active condition, that will be the net earth pressure in that region. Okay, so because in this side is basically void, so there is no counterpart to nullify or to counterbalance this earth pressure, which is basically contributed by region 1 above the dredge level. So above the dredge level and in region 1, whatever active earth pressure will be having, so that will be the net earth pressure on the wall. Okay, it's fine. Now if we move below the dredge level and in region 1, then okay, so it will be better if we basically try to draw the qualitative net earth pressure diagram simultaneously. Okay, so right now we are not considering the water table location, so we'll incorporate this water table effect in the actual problem with the given data. Okay, so now for a cohesive backfill, as you know that for cohesive backfill, for clay, your phi value is 0. So therefore, your active and passive earth pressure coefficient both will be 1. So if this active earth pressure coefficient and passive earth pressure coefficient becomes 1, then what is the distribution of active and passive earth pressure for a purely cohesive soil? So purely cohesive soil, the active and passive earth pressure distribution will be like this. Okay, so here I am writing that PA
நீ சொன்னேன்ல ஒண்ணு
Z
நீங்க வச்சுக்கீங்க ஒண்ணு நான்
will
வச்சுக்கிறேன்
be
அப்படின்னு அது எப்படி வச்சுக்க முடியும்
gamma Z minus
இதுல வந்து ப்ளூடூத் கனெக்ட்
2C,
பண்ணீங்கன்னா ஏதோ ஒரு ஆடியோ தான் வரும்
and
ரெண்டுத்துலயும் ஒரே மாதிரி தான் இருக்கும்.
PPZ will be gamma Z plus 2C, where Z is measured
அப்படியா
from the backfill top.
தெரியுங்களா
Okay, so Z is measured from the
தெரியுதுங்க அப்ப
backfill top. Now, as
எனக்கு
you can
வந்து
see, at the top of this backfill, that is
டிஸ்கனெக்ட்
at
பண்றேன்
Z equals to 0, your first component will be nullified. This component will not be there. So it will be having only minus 2C value. Okay. So you are having somehow a negative pressure at the top of the backfill, and this is having a magnitude of 2C. Now as you go below inside the backfill, so at some depth, this earth pressure distribution will means it will basically shift from left side to right side, that is in terms of magnitude. So this value, this active earth pressure value will be exactly equal to 0, and then it will possess some positive value. Okay, and we can easily determine this depth, and this is known as the tension crack depth Z0, and this value you can calculate from 2C by gamma root K, but in this case this K value basically equals to 1 for a purely cohesive backfill. So therefore this Z0 value you can easily calculate following this equation, 2C divided by gamma root under K, where C is the cohesion of the backfill, gamma is the unit weight of the backfill, and K is the active earth pressure coefficient for the backfill condition. Now at the dredge level and in region 1, so at the dredge level and in region 1, you will be having some positive value from the active side. Now as soon as you move below the dredge level, so one side you will be having active earth pressure, and on another side you will be having passive earth pressure. So from the active earth pressure condition, so you are having the value gamma H minus 2C, or we can say Q bar minus 2C. Now what is the value of Q bar? So Q bar is nothing but, so Q bar, this is nothing but gamma H. Okay, so this height, the height of the cantilever sheet pipe wall. So this is the distribution PAZ gamma Z minus 2C, since active earth pressure coefficient equals to 1. So therefore this Z will be H at this level, and this Q bar will be gamma H. So gamma H minus 2C. And from the passive side, so at this level, at the dredge level, but in region 2, your passive earth pressure will be Q bar will be 0. Okay, so since Z is basically started from this level itself, so Z value is 0. So we will be having only the 2C component. So one side we are having this active pressure as Q bar minus 2C, where the Q bar equals to gamma H, and on the passive side we are having 2C, the magnitude of passive earth pressure. So therefore it's very obvious that at the dredge level itself, this net earth pressure. Okay, so we are basically not drawing the individual active and passive earth pressure distribution for all
Okay.
these regions. We are directly determining the net earth pressure. So therefore, at the dredge level, the net earth pressure will be, what will be the net earth pressure? The net earth pressure will be 2C. This is from this side, from the passive side, and from the active side it is q bar minus 2C. So therefore 2C minus q bar minus 2C. Therefore 4C minus q bar. Okay. So this is the net earth pressure at the dredge level. So net earth pressure at the dredge level, therefore we can see from the discussion that it will basically jumping from the left side to the right side to
Okay.
the
Okay.
left side.
நோட்ல சார் கொடுக்கணும் அந்த சாருக்கு போயிடுச்சு அப்படின்னா சிக்கல் எனக்கு சார் கொடுக்குற வழியே இல்லை.
And this value is your 4C minus q bar. This value, and this value your q bar minus 2C. Okay, so at z equals to 0, region 1, you are having PA value equals to minus 2C, and Z equals to H. In region 1, your PA value is q bar minus 2C, where this q bar equals to gamma H, and Z equals to H. In region 2, I think there is no point to write this individual component, because as you can see very easily that the net earth pressure distribution will be, the net earth pressure at this dredge level would be 4C minus q bar. And how? Because okay, so Z equals to H, your for region 1 already I have written q bar minus 2C, and for region 2 it will be obviously Z equals to, so it will be better to write at DL. Okay, so at DL your Z equals to H for region 1, however Z equals to 0 for region 2, therefore your PP will be simply 2. So therefore your net pressure, if I indicate in this fashion PN, so this is your net pressure, so it will be PP minus PA at the same dredge level, so it will be 2C minus q bar minus 2C. Now you may ask the question that why I have basically subtracted PA from PP, why not PP from PA? So it's because that passive pressure magnitude is very greater than PA. Okay, so that's why it will become 4C minus q bar. Now if we move further, so up to some point in this region, in this portion, your distribution, the net earth pressure distribution will remain same. So it will basically remain same. Why? So it's due to this fact that your PA from the region 1 side, it will be q bar plus gamma Z. Suppose your Z, or rather you can take any value A. Okay, it will be better. So suppose you are measuring some value A. from the dredge level. So therefore, from the region 1 active side, you are having q bar plus gamma a minus 2c, and from the passive side, you will be having gamma a plus. Now, if you take the net of these two, that means pp minus pa, what will be the value? The value will be q bar plus gamma a, gamma a plus 2c minus q bar minus gamma a plus 2c. So gamma a will cancel out, so leaving behind 4c minus q bar. So therefore, as you can see, the net earth pressure distribution will be constant for some certain depth below the dredge level. Okay, so below the dredge level, your net earth pressure distribution will remain constant for some or up to some depth. Okay, so that we don't know, that we will determine subsequently in this problem, and we'll see or we'll determine what will be the net earth pressure distribution at the base of the wall. So at the base of the wall, so at base, at the base you are having basically region 4 at the right side and region 3 at the left side. Now region 3 is under active state and region 4 is under passive state. So therefore, there will be a switch again in the net earth pressure diagram, now from left side to the right hand side. Why? Because passive earth pressure is much greater than the active earth pressure. And what will be the value? The value, this Pn, so Pn would be your basically Pp from the left side, means right side, from region 4, it will be, so if I write in this fashion, Pp4 minus Pa3. So Pp4, it will be basically q bar, that is the vertical overburden up to the dredge level, plus this part. So this dimension is your basically d, the embedment depth. So this dimension is basically your d, embedment depth. So q bar plus gamma d plus 2c. So this is the passive earth pressure from the region 4. And what is the active earth pressure from region 3? So active earth pressure would be gamma d only, minus, because there is no surcharge above the dredge level from the region 3 side. So gamma d will cancel out, and the final expression would become 4c plus q bar. Therefore, as you can see, this distribution now switch from left side to the right hand side, and this value is now 4c plus. Okay, so this is the net earth pressure diagram. This is the net earth pressure diagram. So at the top, I am repeating once more. So at the top, you will be having some negative pressure of magnitude 2c. Then at a depth of z0 equals to 2c by gamma root k, you will be having the net earth pressure entirely exactly 0. Then it will basically have some positive value, and at the dredge level in region 1, so it will be having a value of q bar minus 2c. Then this net earth pressure at the same dredge level, as you move basically from region 1 to region 2, or from right hand side to left hand side, so you will be having a value of 4c minus q bar, and this distribution remains same up to a certain depth. And why? That just now we have basically mentioned or discussed, then it will again switch from the left hand side to the right hand side with a magnitude of 4c plus q bar at the base of the wall as the net earth pressure diagram, net earth pressure on the cantilever sheet pile 1. Okay, so this is the qualitative distribution of net earth pressure on the wall. Now we'll try to figure out the values, means the quantity of each component for the given inputs to this problem. Now first, so the wall is having a total height of 6 meters. Okay, so this is the water table location, and this is the ridge level, and this is the base. Okay, okay. Now we'll first calculate the, okay, so this value is your 4 meter and this value 2 meter. Now we'll first calculate the tension crack depth, Z0. So Z0, it is basically 2C by gamma, because here K and Kp both are 1. So K equals to Kp equals to 1. So 2 multiplied by 35 divided by 17.5. So if you calculate, this value would be 17 divided by 17.5, that means 4 meter. So the tension crack depth will be basically the tension pressure, means the active earth pressure for region 1 will be exactly 0 at the level of water table location. Okay, so it will first start from some value. So this value is your 2 multiplied by 35, that is 70, and then this becomes 0 at a depth of 4 meter. So this is again the value for Z0, and then this is your minus, and the below distribution is your positive. Okay, so this value, your q bar minus 2c. Now what is the value of q bar? Q bar basically effective overburden at the dredge level from region 1 side. This is the effective overburden at dredge level from region 1, because from region 2 it will be 0. So region 1 it will be gamma. Okay, so since we are having the water table in between region 1, so we have to accordingly consider this unit weight. So it's basically gamma h, but for above the water table, we have to take the saturated unit weight, and below the water table, we have to consider the submerged unit weight. Therefore, this value would be 70 plus 15, 85, 50. Okay. So this is the Q bar value. So therefore, this value would be 85 minus 70 equals to 15. Okay, Q bar minus 2C. So just refer to this qualitative distribution, this diagram of net earth pressure distribution. Okay, and here it will be 4C minus, sorry, so this side it will be 4C minus Q bar. So 4C minus Q bar, so this value 4 times 35 minus 85. So 4 multiplied by 35 minus 85, that is 55 kPa. And then it follow a uniform distribution, and then it becomes, it basically changes the side from left to right and having a final value of 4C plus Q bar. That means 225. And this is the net earth pressure distribution. Okay, so this dimension gives the embedment depth. So this is the answer to problem 1. So we have to determine the net earth pressure diagram on the sheet file, and this is the net earth pressure diagram. So it will start from a value of minus 70 at the top of the wall, then it's having a value of 15 at the right hand side at the dredge level, and then it becomes 55 at the left hand side at the dredge level. The net earth pressure becomes, and then it remains constant after a certain depth, and then it switches from left side to right hand side with a value of 225 kPa at the base of the wall as the net earth pressure on the wall. Okay, so this completes the net earth pressure diagram on the given cantilever sheet pile wall in purely clay deposit. Okay, so now we'll move further. So we'll take problem 2. In problem 2, for the cantilever sheet pile given in problem 1, we have to determine the D value that is to be provided assuming an increase of 20% to the theoretical value. So that means we have to determine the embedment depth. First we have to determine the theoretical embedment depth, and then we have to basically put a safety margin on this theoretical value, and we have to report the provided embedment depth. So to do that, first we have to consider only the positive part of the net earth pressure distribution. Okay, so we will not consider any negative earth pressure distribution while calculating the embedment depth. Okay, so to be on the conservative side, so this is the dredge level. So to be on the conservative side, this part will not consider. So this negative distribution will not consider. So we'll basically start from at a depth of 4 meters. That is from the water table location. So this is your water table location. This is 4 meters. This is your 2 meters. And this is D. And this D will basically figure out. Okay. So for that, we'll consider the distribution from the water table location, because this part, the above part, is under tension, and that part will not consider for calculating the embedment depth. So this value is your 15. Okay, so these values we are adopting from the previously determined net earth pressure distribution. So this is 15, and this side it is 55. Okay, so this is your 15 and this is your 55. Then it remain constant up to a certain depth, and finally it becomes 225 at the bottom or base of the wall. So this is the net earth pressure diagram for calculating D. Okay, so it will be better to write in this fashion. This is the considered net earth pressure diagram. Okay, again these values are in it. Now we have to basically do two things. So first we have to basically take the force equilibrium in the for the system, and then we have to consider the moment equilibrium about the base of the system. Okay, so these two things we have to satisfy for the given system. So first we have to consider the force equilibrium in the horizontal direction for the given cantilever sheet pile wall, and then we have to take the moment of all the forces which are basically acting on this system above the base of the wall. So by satisfying these two conditions, we can easily get the value for D. How, that we'll see subsequently. Okay, so first we'll first introduce some variables. So these variables are, for example, so this is the active earth pressure. So this active earth pressure, so this is the, okay, so this is the resultant of active earth pressure. So this part basically represents the active earth pressure distribution on the wall from region 1. Okay, and this is the resultant of the PA is the resultant of the active earth pressure, this active earth pressure distribution, and this is acting at a height of y bar from the dredge level. So from the dredge level, lever arm of this active resultant active earth pressure is y bar. So these are the two variables that just now we have introduced. Now we'll basically extend this rectangular distribution up to the base of the wall. So suppose this is your point B, this is your point A, this is your point C. Okay, C represents cohesion, therefore we can use a separate value D. This is your E, this is your F, G, H, I, and J. We have named the entire distribution in this fashion. Now for horizontal force equilibrium, means from condition 1 or criteria 1, what will happen? Your PA plus P triangle minus P rectangle should be 0. Why? Because so this triangle right now we are considering. Okay, so this triangle, so we are taking the resultant of this triangular distribution as the triangle. Triangle in the sense H, I, J. And we have also considered this rectangular distribution. So this rectangular distribution, okay. So this is we have considered P rectangle, and the rectangle here D BD GI BD GI BD GI. So we have basically considered this region. This region is not originally in the distribution. This region was not originally in the distribution. So when we considered P triangle, so we have considered this region for the positive contribution, and when we have considered P rectangle, we have considered this shaded region as the negative contribution, means on the negative side. So positive and negative, so this will basically balance each other, and therefore it will not create any problem for the force equilibrium condition in the horizontal direction. Okay, so the entire distribution we have basically splitted in this fashion. So one active earth pressure, resultant active earth pressure, one is P triangle, triangle in the sense HIJ. So this is the triangle, and the rectangle is BDGI. So this is the rectangle. So therefore this will be the force equilibrium equation for the horizontal direction. PA plus P triangle minus P rectangle equals to 0. And next, okay, so for that we'll introduce one more variable, and that is called Z. Okay, so this is the height of this triangle. So this is the basically height of this triangle HIJ from the base of the wall. Now, considering this equation 2, what will be the moment equilibrium equation about the base of the wall? So it will be PA multiplied by D plus Y bar plus, so D plus Y bar, this is the lever arm of the resultant PA, active earth pressure resultant PA from the base of the wall. So the embedment depth is your D, and Y bar is basically measured from the dredge level. So D plus Y bar will give you the total lever arm from the base of the wall for resultant active earth pressure PA. Then P triangle multiplied by the corresponding lever arm. Now what will be the corresponding lever arm? So it will be simply Z by 3. Then minus P rectangle into D by 3 equals to 0. Because the CG of this triangle lies at a height of Z by 3 from the base of the wall, and for the rectangle it lies at a height of D by 2 from the base of the wall. Now these two equations, that is equation 1 and equation 2, these two equations we have to solve to get the value of D, and that should be the theoretical D value. Then we have to multiply it with 1.2 to get the provided value for the embedment depth of the given cantilever sheet pile wall. Okay, so we will do one by one. Okay, first we'll calculate this value. So we'll start from PA. So PA, this will be the area of this triangle, and here the base value is your 15 and the height is your 2. So therefore this PA will be half multiplied by 15 multiplied by 2. So therefore 15 kilonewton per meter. Then P triangle. So P triangle, again this is a triangular distribution. So the area of this triangle will give you the force. So now what are the dimensions of the triangle? The base value is 225 plus 55 and the height is Z. Okay, we have assumed this value, the Z, the height of this triangle as Z. So 225 plus 55 multiplied by Z. So therefore 140 Z kilonewton per meter. And then P rectangle. So P rectangle, it's simply 55 times T per meter. Now from equation 1, we will be having 15 plus 140Z minus 55T equals to 0, or Z we can represent in this fashion: 55T minus 15 by 140. Okay, so this is the expression for Z, that is the height of lower this triangle P triangle in terms of the embedment depth of the wall. And from equation 2, now to get to go for equation 2, we'll first calculate this lever arm Y bar, the value of Y bar. So Y bar, so it will be simply 2 by 3, because the height of the triangle is 2 and we are measuring this CG from the base of the triangle. So therefore it will be 2 by 3 meter. So therefore, obviously from equation 2, this will be PA, that is 15 multiplied by D plus 2 by 3, then plus 140Z into Z by 3 and minus 55D into D by 3, D by 2 equals to 0. Okay, so this is the equation for moment equilibrium. Now we'll substitute the value of Z from equation 3. Suppose this is your equation 3. So we'll substitute the value of Z in terms of D from equation 3. So it will become 15 D plus 10 plus 140 by 3 Z square. Now Z square means 15 D, 55D minus 15 divided by 140 square minus 55 by 2. This is after substituting the value of Z from equation 3. Okay, now as you can see, okay, so now as you can see that this is a simple quadratic equation in D. Okay, so if we simplify this equation, equation 2 further, then it will become 8525D square minus 4650 times D minus 4425 equals to 0. Okay, suppose this is your equation 4. Therefore, equation 4, after algebraic simplification, this equation 4 we have got, and equation 4 is nothing but a simple quadratic equation in D. So therefore, if we solve this equation, we can easily determine the value of D from this equation. So after solving, I am not solving this equation here, so you can solve this equation at your home. So after solving equation 4, so D value would become 1.04 meter. Okay, so this will be the solution of equation 4. So based on solution of equation 4, we have got the value of D as 1.04 meter, but this is the theoretical value. Please keep in mind, so whatever value we have got after solving equation 4, so this is the theoretical value. But in actual scenario, since we have to basically keep some safety margin, so therefore the provided D value, D provided, would be 1.20% greater than this theoretical value. Therefore 1.2 times the D theoretical. So that means 1.2 times 1.04, and it will be 1.25 meter. So this is the, so the value 1.25 meter embedment depth we should provide for the given cantilever sheet pile wall. So in this way we can calculate the provided D value. Okay, so we have to basically first determine the net earth pressure diagram for the given cantilever wall, then we have to satisfy two basic conditions. The first one is the force equilibrium equation or force equilibrium condition for the horizontal direction, and then the moment equilibrium condition about the base of the wall. Now by satisfying these two conditions, we'll be ending up with two equations, and if we solve these two equations, we can easily determine the theoretical d value first, and upon multiplying this theoretical d value with the given safety margin, that is 20% here, so 20% more value we have to provide, so therefore 1.2 times the d theoretical will give you the d provided in the actual scenario, and this value is 1.25 for the current problem. Okay, now we'll take our next problem, that is problem 3. So in this problem, an anchor sheet pile in a pure sand is shown in the below figure, and consider that the anchor force F is acting at a depth of 1 meter from the ground surface. So we have to compute the d value that is to be provided, assuming an increase of 20% to the theoretical value. Okay, so the same philosophy will basically adopt for this problem as well. However, to determine the net earth pressure diagram, the rotation of the wall will be slightly different as compared to the previous scenario. So in the previous scenario, we have considered, or we were given, a cantilever sheet pile wall. Now in this problem, it's given the anchor sheet pile wall. Okay, so an anchor sheet pile is basically given. So therefore, first we'll see what is the deflected pattern. So what is the mode of rotation? So for an anchor sheet pile wall, the wall will basically rotate about the anchor level. Okay, so this is the anchor. So with respect to this anchor, the wall will basically rotate. And please keep in mind, for this time being, we are basically considering the free earth method. So this is based on free earth method. So therefore, again, based on the deflected pattern of this wall, we can divide this soil mass, entire soil mass region, into some categories, okay, into some zones. So for example, this soil portion above the anchor level will be under which condition, active or passive? So it will be under passive condition, since the wall is basically moving towards the backfill, and this part will be under active condition, means the right hand side of the soil mass below the anchor will be under active condition, and left hand side of the wall below the ridge level will be under passive condition. However, for simplicity, since this portion, this soil mass portion is very less, okay, so we'll basically consider only two scenarios, only two conditions, that the right hand portion will be entirely under active condition and the left hand portion will be entirely under passive condition. So therefore, this will basically simplify the net earth pressure distribution on the wall, and how that we'll see. So we'll not discuss in much details about the net earth pressure distribution, because for this problem, it's basically the deposit is purely sand, and this kind of problem already we have solved in the last week for cantilever sheet pile wall. So we'll first basically draw the active earth pressure or net earth pressure distribution up to the ridge level for the right hand portion. Okay, so this portion is basically void. This is void. So therefore, we'll be only having the active earth pressure as the net earth pressure in this region 1, that is the right hand portion and above the ridge level. Okay, so we'll try to determine the net earth pressure diagram first. So the wall is having now a total height of 6 meter, 10 meter. So first let me locate the water table location. This is the water table location, and this height is 6 meter, and this height is 4 meter, and this dimension is your D. Okay, so this is the embedment depth. Now what we have seen from the last session, that the active earth pressure distribution will start from a value of 0. So first let me draw the qualitative distribution part. So this will be 0 to some value at the water table, then it will vary in this fashion, and then the net earth pressure becomes 0 at a distance of or depth of A prime, at a depth of A prime, this distribution, the net earth pressure becomes 0. And then earlier, so we'll first draw the distribution for the previous case, that is for cantilever sheet pile wall. So for purely cohesionless soil, for a cantilever, given cantilever sheet pile wall, the net earth pressure diagram looks like this. Okay. However, there will be a slight change in the diagram due to this anchoring condition. Okay. So this anchor force I didn't show earlier. So it's basically at a depth of 1 meter from the ground surface. Now, due to rotation about this anchor level, we have divided the region into two parts, the entire soil mass. So the left side portion will be under passive condition, and the right hand side portion will be under active condition, as shown in this slide. Okay, so therefore up to the dredge level, the right hand portion, means above the dredge level in the right hand portion, the active earth pressure will be the net earth pressure. Now as soon as we move below the dredge level, so in one side we are having passive pressure and another side we are having active pressure. So therefore the net pressure will be the difference between these two, passive and active. And as you know that the passive pressure, the magnitude of passive pressure is very, very large or very, very high as compared to the active pressure. So therefore the distribution will basically shift from right side to the left side. Now earlier at the base of the wall, this active and passive conditions will also change. Means right side we were having passive and left side we were having active. But this is not the case. Active and passive, these two conditions are already fixed. So the right hand portion will be entirely under active, and the left hand side will be entirely under passive. So therefore this distribution will not switch again. Okay, so it will basically keep on increasing. So this value will keep on increasing on the left portion itself. So this will be the net earth pressure diagram. This is the net earth pressure diagram for an anchored sheet pile wall in purely positionless soil. Now we'll determine the values. So first, at the water table location. So for that, first we need to know what are the coefficients of active and passive earth pressure. So active and passive earth pressure, so Ka, so it will be 1 minus sine 35 divided by 1 plus sine 35. So therefore, I hope 0.271. And the coefficient of passive earth pressure 1 plus sine 35 divided by 1 minus sine 35, therefore 3.690. So these are the two values. Now this active earth pressure at the water table location, so it will be simply Ka gamma z. So Ka value is your 0.271, gamma, what is the saturated unit weight is 17.5 above the water table multiplied by 6. So therefore this value would be 0.271 into 17.5 multiplied by 6, so 28.46 kPa. 28.46. So this is in kPa. Distribution is in kPa. Okay. Now, due to the water table, what will happen? The unit weight will now change. Means below the water table. So above water table, it will be governed by the saturated unit weight. However, below the water table, it will be governed by the submerged unit weight. So therefore, this 28.46 will remain constant, and in addition to that, so this value, that is due to the overburden in this region, will get. So what will be this value? So this value would be 0.271 multiplied by 7.5 multiplied by 4. So therefore 28.46 plus 8.43. So 28.46 plus 8.13. So therefore the final or total active earth pressure at the dredge level from the right hand side is 36.59. Okay, 36.59. Now what is about the A prime value? How to calculate? So already we have learned in the last session how to calculate this A prime. So A prime we can calculate by equating the net earth pressure as 0, and by equating the net earth pressure as 0, we'll get we basically got this kind of expression, that A prime is your PA divided by KP minus Ka gamma prime. Now what is PA? So PA basically this value, that is the active earth pressure at the level of, at the ridge level. Okay, so this is basically denoted as PA. So therefore this A prime value would become, so we know PA, we know KP, Ka and gamma prime, so we can easily calculate the depth A prime from the ridge level where the net earth pressure becomes 0. So 36.59 divided by 3.69 minus 0.271 multiplied by 7.5. Okay. So this will give you the A prime value as 1.43 meter. This value is your 1.43 meter. So therefore, this value is 1.43 meter. So at a depth of 1.43 meter from the dredge level, we are having the net earth pressure as 0. Now, this net earth pressure will go on increasing, okay, on the left hand side. Now what will be the final value? The final value at the base. So this final value, so for that we'll basically introduce a variable. This is the height of this triangular distribution, and this is the total depth of embedment D, that is I plus A prime. Now this distribution basically follow a variation as Kp minus Ka, that is the net earth pressure coefficient, into gamma prime into Y. Okay, so this would be the earth pressure, the net earth pressure at the base of the wall. Now this basically completes the net earth pressure distribution on the given anchored sheet pile wall. Now what we'll do, we'll basically follow, or we'll try to satisfy the two conditions, okay, similar to the previous problem. So the first one is the force equilibrium for the horizontal direction, that is summation of Fh equals to 0, and the next one is summation of M base equals to 0. Now if we basically try to okay, so before satisfying these two conditions, we'll try to calculate the resultant active thrust. Okay, so the resultant active thrust, so only this part, so up to this part. Okay, so suppose this is the resultant active thrust Pa, and its location from the net from the point where the net earth pressure becomes 0. This is your basically Y bar. Okay, sorry, unlike the previous problem, we have to modify one thing here, basically, that is, we have to basically take the moment about the anchor level, not about the base. Okay, now for this problem, since the wall is basically rotating about the anchor, so we have to take the we can basically take the moment equilibrium above the base, but in that case the problem will be indeterminate, because this F force will come into picture, and with these two equations but with three unknowns, we can not solve the system of equations, which will be basically resulting from satisfying the moment and force equilibrium conditions. So therefore we will basically take the moment equilibrium in such a way so that the system of equations and the number of unknowns will become equal. So the number of unknowns here, as you can see that first we have to determine the depth of embedment, and then we have to determine the force which is basically acting in the anchor. So two unknowns are there. Okay, and if we take basically the force equilibrium about this F, about this anchor level, so this if its line of action is basically acting along the same line, so the lever arm of this force F becomes automatically 0 and it will not come into picture. Okay, so therefore the moment equilibrium is taken about the anchor level, not about the base level, just to erase this part, this force F in the resulting system of equations. Okay, nothing else. Okay, but before that, we'll try to calculate this resultant active earth pressure PA and its lever arm from the point of 0 net pressure. So, and this part also we have solved in the previous session, so will not take much time to solve this part. So, we'll quickly calculate the resultant active earth pressure and then its lever arm from the point of 0 net pressure. So for that, we'll first divide this distribution, this active earth pressure distribution, into 4 components, that is 1, 2, 3 and 4, where 1, 3 and 4, these are the triangular components and 2 is the rectangular component. Okay, so this is calculation of PA and its lever arm y bar. First, coming to component 1, the force will become half into 6 into 28.46. So half into, okay, so let me put the heading here. So this is your PAI and this is your YI bar. This is in meter and this is in kilonewton per meter. Okay, so suppose this point is your O, therefore this is measured from O. Okay, so for component 1, it's half multiplied by 28.46 multiplied by 6. So this will give you the value as 85.38. Then component 2, that is simply a rectangular distribution. So 28.46 multiplied by 4. So that means 113.84. Then for component 3, it will be 8.13. So half multiplied by 8.13 multiplied by 4. So therefore 16.26 kilonewton per meter. And lastly, half multiplied by the total base value is here 36.59 multiplied by the A prime value, that is 1.43. So this will give you 26.16. Okay, now the resultant PA, it will be the summation of PI bar PAI, so it will be 241.64 kilonewton per meter. Now we will calculate the corresponding lever arm as well. So for component 1, and please keep in mind we are basically calculating the lever arm from the point of 0 net earth pressure. Okay, so therefore for component 1, it will be A prime plus 4 plus 6 by 3. So A prime is your 1.43 plus 4 plus 6 by 3. So that means 7.43. Then 1.43 plus 4 by 2, that means 3.43. Then 1.43 plus 4 by 3, that means 2.76. And lastly 2 multiplied by 1.43 divided by 3, therefore 0.95. Okay, so this completes the individual active force and the corresponding lever arm calculation. Now we'll try to determine the lever arm of the resultant active force. So it will be simply summation of PAI, the product of summation of PAI YI bar divided by summation of PAI. Therefore 85.38 multiplied by 7.43 plus 113.84 multiplied by 3.43 plus 16.26 multiplied by 2.76 plus 26.16 multiplied by 0.94 divided by 241.64. So if you calculate, then this value would become I of 4.53 meter. So this value would be 4.53 meter. So this value is 4.53 meter. Now when we'll take the moment about this anchor, so the lever arm will change. Okay, so we'll again consider basically two forces. So we'll consider this PA and this force as PB. Okay, from the left hand side. Now what are the lever arm of this PA and PB with respect to this anchor level? From the anchor level, so from the anchor level, this would become, if we assume Y1 bar, and for PB will consider this value, this lever arm value, as Y2 bar. So since the distribution basically now we have split it in this fashion, so it will basically involve two resultant forces. So PA from the right hand side and PB from the left hand side, and the lever arm of these two forces with respect to the anchor level are Y1 bar and Y2 bar respectively. Now we will calculate Y1 bar and Y2 bar. Okay, in addition to this PA and PB, there is one more force, that is the anchor force. Okay, the force which is basically acting in the anchor. Now to calculate this Y1 bar and Y2 bar, since we know Y bar, so with respect to this Y bar we can easily calculate the Y1 bar. So Y1 bar, so this value would become, so we'll first calculate the depth of this zero net pressure from the ground level. Okay, so this is the ground level. So from the ground level, we'll calculate the depth of the point where the net pressure becomes zero. Now what will be that depth? 6 plus 4 plus a prime. Okay, so a prime value is your 1.43. Now we'll minus the location of this anchor from the ground level, so that is 1. So that will give you this side y1 bar plus y bar. Okay, so y1 bar plus y bar. This is nothing but y1 plus y1 bar plus y bar. Now we'll again minus this y bar value. We have just now calculated it as 4.5. Okay, so are you able to follow me? First we have calculated the depth of zero pressure, the depth of net pressure as 0 from the ground level, and it is 6 plus 4, that is the height of the wall, plus a prime. Okay, so this is basically height of the wall h, and this is a prime. Now this will give you the depth of the point where the net pressure becomes 0 from the ground level. Now we have deducted the location of the anchor, that is 1 meter. So this is the location of anchor. Now this will give you summation of these two, y1 bar and y bar. Now if you subtract this y bar from this, so you will easily get the y1 bar value. Okay, and this value would become, I hope this value would be, so 10 plus 10 minus 4.53, therefore 5.47 meter. And y2 bar, it will be simply 6 plus 4 plus d minus 1. So this is the total height plus the embedment depth minus the location of anchor minus its CG from the base. Okay, so its CG from the base is third y. So therefore this will be 9 plus t minus 2/3. Okay, I think I have missed another point here. So it will be better to represent it in terms of y. So therefore this will be 6 plus 4 plus a bar plus y minus 2/3 of y. Okay, oh sorry, 6 plus this part is basically your 2/3 y. Now you basically determine up to this level. Okay, so that is 6 plus a prime minus 1 plus 2/3 y. So that means 6 plus a, this is your 10 minus 1 9 plus 1.43, that is 10.43 plus 2/3 of 1. So this is the lever arm for force B. Okay, so this force PB and this is PA. So we have first determined the depth of the point where net earth pressure becomes 0 from the ground level, and that is 6 plus 4 plus a prime. So this is the depth of the point where net earth pressure becomes 0 from the ground level, but we have to calculate it from the anchor level. So therefore we have deducted the anchor level location from the ground level, and this is 1 meter for this problem, and then we have added this CG of this triangular distribution from its apex, and that is 2/3 of y, because y is the height of this triangular distribution. Okay, now we have got the lever arm and the respective forces involved in this system. Now we'll take the horizontal force equilibrium and the moment equilibrium one by one. So first, for the force equilibrium in the horizontal direction, we'll get PA plus, okay, this represent as PB. Okay, so PA minus PB minus F equals to 0. So therefore your F, you can calculate it from the expression PB minus PA. However, so far we know the PA value. The PA value is 241.64 kilonewton per meter, but PB we don't know. Okay, so PA is your 241.64 kilonewton per meter, but PB we don't know. So PB, we just know the analytical expression. So it's half times Kp minus Ka gamma bar y into y, area of this triangle. So half Kp minus Ka gamma bar into y, and Kp is your 3.69, Ka is 0.271, gamma prime is 7.5, then y square. So after calculation, this value would become 12.82 y square. So therefore this anchor force, it will become 241.64 minus 12.82 y square. Okay, so determination of y is very, very essential to know the anchor force, the value of anchor force. Okay, so that is the height of the lower triangle. So this triangle. Now we'll consider the moment equilibrium. So summation of m about the anchor is 0. So what will happen? So it will basically give you PA multiplied by y1 bar minus PB multiplied by y2 bar equals to 0. So PA multiplied by y1 bar plus PB multiplied by y2 bar equals to 0. Now this PA, this value is 241.64, y1 bar we have calculated it as I hope we have calculated it as 6 plus 4 plus 1.43 minus 1 minus 4.53, so 5.9. Okay, so this value is your 5.9. So this is 5.9 minus the PB. The analytical expression is 12.82 y square. Then multiplied by y2 bar. Now what is the value of y2 bar? Y2 bar is 10.43 plus 2/3 of y. So 10.43 plus 2/3 of y. So if you simplify, okay, for your easy convenience, I am writing the lever arm, the values of lever arm here. Y1 bar is your 5.9 meter and Y2 bar 10.43 plus 2/3. Okay. Now, if you simplify this equation, then you will basically end up with one equation, one cubic equation in y. So suppose this is your equation 1. So equation 1, this is basically a cubic equation in y, and if you solve this equation, so you can get the value of y. So after solving this equation 1, again I am not solving this equation here, so you can try at your home. So it's a very straightforward solution. So if you solve this equation, you can get the value of y as 3 meter approximately. So therefore, the theoretical embedment depth will be y plus a bar. Already I have shown, na? So where the theoretical embedment depth as y plus a bar. This a bar, this is the depth of point where the net earth pressure is 0 from the ledge level, and y, this is the height of this triangle. So therefore, this y value we have calculated as 3, and a prime already we have calculated. So a prime value is your 1.43. So 1.43. Therefore, 4.43 meter. This is the theoretical embedment depth. But to get the provided depth, the depth which should be provided in the actual scenario, we have to multiply this theoretical embedment depth with 1.2. We are providing 20% more value, okay, to be on the conservative side. So this will give you the value as 5.3 meter, and this should be the answer. So if you don't have any confusions or doubts so far, so we'll move further. So we'll take problem 4, and this is basically a continuation of problem 3. So in problem 3, we have determined the embedment depth, the actual depth which should be provided in the practical scenario by considering 20% more value of the theoretical depth. Okay, now in this problem we'll try to determine the depth of the anchor, where this anchor should be placed. Okay, so earlier we have considered this depth of this anchor as 1 meter from the ground surface. Okay, so this was basically given to the problem statement itself. However, we can calculate this anchor. Okay, so we can calculate the depth of this anchor by following this philosophy, that this is the ledge level, this is the ground level. Since this right hand part is under active condition, so the rupture surface or the failure surface will be inclined at an angle of 45 degree plus 5/2. So this angle will be 45 degree plus 5/2. Now we have to draw perpendicular from this point where the rupture surface basically intersects the ground level. So this angle will be 90 degree. Now we have to basically provide the anchor which will be above this line. Okay, this line. The line dotted in red color. So this is the horizontal location. Now coming to the vertical location, suppose this height is B and the total height from the ground level is your HE. Okay, and one more condition, that is we are considering that this B value is your HE by 2. And what would be the plan view? So if this is the sheet pile line, and if this is the system of anchor, and obviously this is the continuous anchor case. Okay, so as mentioned in this problem, consider that the anchor is continuous. So therefore, if this is the horizontal spacing S and this is also S, so this is the plan view. So the length of one anchor would become S. So S by 2, S by 2. Okay, so this value is your S by 2 and then this value is your S by 2. So S by 2 plus S by 2, L would become S. Now what we'll do, we'll try to determine the earth pressure diagram for this anchor width. Okay, so suppose this is the anchor and this is basically placed at a depth of HE by 2 and this height also HE by 2. So this is the ground, this depth HE by 2 and this B HE by 2 as assumed. Okay, we have assumed this. Now what will happen, since this force will act in this manner, so the anchor is basically moving in this direction, so this part will be under passive condition and this part will be under active condition. Okay, so this part will be under passive condition, left hand part, and the right hand part will be under active condition. Now considering this, so the earth pressure distribution Okay, so this is the passive earth pressure distribution. And for the active earth pressure distribution, so we will consider the earth pressure distribution only for the anchor width. Now this value is your 0.5 gamma kp Hg, and this value is your gamma kp Hg. So similarly, this value 0.5 gamma kg, and this value 0.5, no, not 0.5 gamma kg. So we can determine the net force, that is by subtracting PA from PP. So where we'll calculate one component, then we can easily calculate the another component. So PP, it will be your Hg by 2 half multiplied by 0.5 plus 1.5, sorry, 1 gamma kp Hg. So therefore 1.5, that is 3 by 8 gamma kp Hg square. So similarly, your PA will be, only you have to consider the active earth pressure coefficient, so 3 by 8 gamma k H square. So the net pressure, so this will be 3 by 8 kp minus k gamma H square. So 1 by 2.67 kp minus k gamma H square. Now this is per kilonewton per meter. Okay, so this force is basically kilonewton per meter. Now what you have to basically do, you have to basically equate this net pressure with the anchor force. Okay, so this net force, so your Pn multiplied by S, sorry, L, so this is the net force, and that you have to equate basically with F, this is the anchor force, multiplied by S, that is the total anchor force, so F multiplied by S, and we'll consider some factor of safety, okay, to be on the conservative side. So we are increasing the anchor force. Now for the continuous case, so this is the when your anchor is continuous. So for the continuous case, your L becomes S. So this L and S will cancel out. So therefore your Pn would be simply F multiplied by factor of safety. Now Pn is your 1 by 2.67 kp minus k gamma H square, and it will be F times factor of safety. So therefore H you can easily calculate from this equation, and this is the objective of this problem. So F times factor of safety divided by multiplied by 2.67 divided by gamma Kp minus Ka. Okay. Now, what are these values? So A, okay, factor of safety, this is given as 1.5 for this problem. Gamma 17.5 kilonewton per meter cube. Kp 3.69. Ka 0.271. And what is the value of F? Since this is a continuation of problem 3, so this F value we can calculate from this equation, 241.64 minus 12.82 y square. So 241.64 minus 12.82 y square. Now y square we have calculated already. So the value of y, y. So the value of y we have calculated as 3 meters. So we'll substitute this value here. So 241.64 minus 12.82 into 3 square. So this is from problem 3. Okay, please keep in mind. So this value would become 126.26 kilonewton per meter. Now we'll substitute these values one by one in this equation to get the final answer. So if just now we have calculated 126.26, factor of safety 1.5, 2.67 divided by 17.5 multiplied by 3.69 minus 0.271. So the answer is 2.91 meter. Okay. Now as you can see, earlier in problem 3 we have considered, or it was given, that the anchor is basically located at a depth of 1 meter. But here what we can see, that the anchor is basically should be placed at a depth of what? So this total value is your 2.91. Okay, so suppose we are considering 3. So this part is your 1.5. So this part is your 1.5 He by 2 plus He by 2, He by 4. So that means half plus 1 by 4. So 3 by 4 He. So 3 by 4 multiplied by 2.91. So that is 2.2 meter. So now the location comes as 2.2 meter. Okay. So this is the location. Now if this is the location, therefore the calculation which already we have done for problem 3, so that will be basically impacted, since the anchor should be placed at a depth of 2.2 meter instead of 1 meter, which was given in the previous problem. So therefore the calculation so far we have done, so that will be impacted. So we have to basically calculate those values, or we have to repeat those calculations with this new value of the location of anchor, and we have to check whether the provided d value is safe or not. Okay, based on this revised calculation. So we'll not do this calculation again and again here, because this is basically a repetition kind of thing. So I'll request all of you, so this is a homework, and check that whether, or please recalculate the D provided value. Okay, so with this new location of the anchor. So earlier the location was at a depth of 1 meter from the ground level, but now it becomes 2.2 meter from the ground level. So with this new location of the anchor, please recalculate the D provided value. Okay. Okay. Now, two more problems are there, so we'll solve quickly. So for problem 5, we have to determine the axial force in start B shown in the figure below, and the center to center spacing of the starts along the length of the cut is 2.5 meter. The soil is steep, fissured clay, and the unit weight of the soil is 19 kilonewton per meter cube, and the cohesion of the soil is 40 kilonewton per meter square. So this is the geometric configuration of the breast excavation, as you can see. So this excavation is basically supported by 3 starts at different levels, start A, start B, and start C. And we have to basically determine the axial force in start B. Okay, and these starts are basically arranged in a fashion that the center to center spacing between these starts along the length of the excavation is 2.5 meter. That is, the horizontal spacing is 2.5 meter, and the vertical spacing is given as, what is the vertical spacing? The vertical spacing is given as 2 meter. Okay. Now how we can determine? So to determine this axial force in the start B, first we have to know what is the earth pressure distribution on this wall, sheet pile wall. And depending on the type of soil, we can have different distribution for the earth pressure as shown in this slide. So for sand, it will be a rectangular distribution. For steep fissured clay and soft to medium clay, it will be something like a trapezoidal distribution. However, depending on the value of gamma h by c, you have to figure out, or you have to identify which distribution should be appropriate for the given scenario or condition. Okay, now for that, we'll first calculate the value of gamma h by c. So gamma value here is 19 kilonewton per meter cube. The height of the excavation is 2 plus 2 plus 1 plus 1, that is 6, and the cohesion value is your 40. So therefore, this gamma h by c ratio is coming out to be 2.85. Okay, so which is less than 4. Therefore, out of these 3 distribution, we have to choose this one. So this one would be more appropriate for the given condition. Okay, where the distribution is starting from a value of 0, then it's reaching a value of 0.3 gamma h. Okay, so as you can see, the magnitude of the pressure is varying from 0 to gamma h to 0.4, 0.2 gamma h to 0.4 gamma h. So for this calculation, we'll consider an average value of these two. That means 0.2 plus 0.4 divided by 2, that is 0.3 times gamma h. Okay, so either you can go for 0.2. So for that, you will be on the oversafe side, unconservative side, and if you consider 0.4 times gamma h, it will be you will be on the conservative side. So here we considered an average value of these two, that is 0.3 times gamma h, and this is the appropriate distribution for the given problem scenario. Okay, so now what we'll do, we'll basically consider the free body diagram. So since this is a symmetric problem, so we'll consider the free body diagram starting from the ground level up to point B. And if we again start from the base of the excavation up to point B, so this is basically symmetric with respect to this point B, the start level, the start B, the distribution is symmetric. So if we consider one half of this distribution, either a lower or upper half, and if we add the reaction at the level of B, then we will get the total axial force in start B. So this would be the philosophy. So since the distribution, active earth pressure distribution is symmetric, you can consider either the lower half or the upper half, and considering these two halves individually, you will basically get a reaction force at the start level B, and if you add these two reactions, you will get the total or final axial force in start B. Okay, so for this problem we'll consider the upper half, that is starting from the ground level. So this is your reaction in B, and this is reaction at A. Okay, so we will be having two reactions, RB prime and RB double prime. So RB will be a summation of these two, RB prime plus RB double prime, and this will give you the axial force in start P. Now how the distribution looks like? So the distribution, okay, so this is your 1 meter, and this distance is your 2 meters. Okay, and this value is your 34.2 kilonewton per meter square. Okay, so suppose this is your point T and this is your point A. This is your point T, and this distance is your 1.5 meter. Now what we'll do, we'll calculate the resultant of this triangular part. Okay, so triangular part, this is this triangular part, suppose this point is your G. So it's triangular distribution, so triangular distribution, the resultant for this triangular distribution is your half 1.5 multiplied by 34.2. Okay, so this part this hatch portion part, this is your half multiplied by 1.5 multiplied by 34.2. Now where it acts, so it basically acts at a distance of h by 3 from this side. Now what is the height of this triangle? So height of this triangle is your 1.5. So 1.5 divided by 3, that means 0.5 meter. And what is the location of this point Z from A? So this is also 0.5 meter. So if you can clearly see or carefully observe, then this value would be also 0.5 meter. So therefore the resultant of this triangular distribution is directly passing through the reaction or this level, this point A. Okay, this is the resultant, which is a value of half multiplied by 1.5 multiplied by 34.2, and this is directly passing through this level, this location or start level A. Now what we will do, we'll basically try to take the moment about A. Okay, now if we try to take the moment about A, then this RV multiplied by this distance 2 meter will have to be balanced by this portion, because the resultant is simply passing through this point. So therefore there will be no movement. Okay, so the location, the lever arm would become 0. So therefore this resultant load will not create any movement. So this RV, so this will basically create some movement, and this is in anti-clockwise direction, and this force, the applied force, the applied active pressure will create some movement in the clockwise direction. So therefore this movement should be balanced by this movement, the movement created by the active force. So therefore this will be 34.2 divided by, now what is this distance? So this distance is again 1.5 meter. Okay, so 1.5 multiplied by, now what is the CG of this distribution? So the CG is basically here, suppose. So how to get this dimension or distance? So this is at a distance of 0.75 meter. Okay, so this distance is 0.75 meter. So 0.75 plus 0.5, so 1.25. 0.75 plus 0.5. Therefore RV, this value would be 64.12 divided by 2, that means 32.06 Newton per meter. Okay, so this is RV prime. Since we have considered only the upper half, okay, so we have got this RV prime value as 32.06 kilonewton per meter. Now similarly, from the FBD of the lower up portion, okay, so we have just now considered the upper up. Now if we consider the lower up portion, BCF, so this is your B, this is your C, this is your A. So we'll get the RB double prime, and it should be equal to RB prime, since it's symmetrical. The distribution, the active earth pressure distribution is symmetrical with respect to start P. Okay, so therefore it will be again 32.06 kilonewton per meter. So therefore RV should be a summation of these two values, RB prime plus RB double prime. So 2 into 32.06, so therefore 64.12 kilonewton per meter. Now this is the force per meter, and if we try to get the total force, so we have to multiply this per meter force with the horizontal spacing. Now what is the horizontal spacing? The horizontal spacing is 2.5 meter. So therefore the total force AP, so you have to multiply this RB with the horizontal spacing SH. Okay, so 64.12 multiplied by 2.4, 2.5, that is 160.3 kilonewton. So this is the total axial force acting in this strata B. Okay, so this is the total axial force which is basically acting in strata B. So in this way you can calculate the start force. Now one homework is pending for you, and that is please calculate the maximum moment in the wall. Okay, because to design this system you should know what are the forces, axial forces acting in the strata, then what is the moment inducing in the wall and the Euler beam. Okay, so these are the Euler beam and this is the wall. So these three things you should know before designing this kind of system: the axial forces in the strata, the moment in the wall, and the Euler beam. Now right now we have solved how to calculate the axial force acting in the strata. So and again only for strata B, not for A and C. So this is very simple, the methodology should be same. So in this way we have to basically approach to calculate the force first in the strats, and then you can calculate the moment which are inducing in this Euler beam and the wall. So this is one homework problem for you. Please calculate the maximum moment in the wall. And this is the last problem for this session. So this problem will end. So this is a rigid pipe with an outside diameter of 30 centimeter, and it is to be laid in a ditch which is 1 meter wide at the top of the pipe, and it's to be covered with 8 meter of compressible soil backfill, where the unit weight is given as 19 kilonewton per meter cube. Determine the load on the sware and take this coefficient K times mu as 0.12. Now this is an example for underground conduits. Okay, and this is a ditch conduit, an example of ditch conduit. So here to calculate the load on the conduit, that is the sware pipe, so we'll first calculate an elemental slice at a distance of z from the ground surface, and the thickness of this slice is dz. Okay, so the elemental slice of thickness dz and with b is considered at a depth of z from the ground surface. Now please carefully observe what are the different forces acting on this slice. So at the top, sigma b times b, it is acting at the top of this slice. Then at the bottom surface of this slice is sigma b plus d sigma b multiplied by b. So these two forces are basically acting from two different surface of this slice, and obviously the weight of this slice. Now due to the application of this load, when it will try to move, so these are the rupture surface. Okay, so for simplification we have considered, or we can consider these rupture surfaces are purely vertical. Now when it will try to move, so since this soil is basically compressible soil backfill, so this theory is basically governed by soil arching. Now what is soil arching? So soil arching is basically a phenomena or a mechanism where the stress is basically transferred from relatively greater yielded region to relatively less yielded region or unyielded region. So this is the yielding portion. Okay, so this is the yielding portion. So this is the yielding portion, since this is compressible soil backfill over the conduit, and these are the non-yielding portion. Similarly, this side also non-yielding, and these are the slip surfaces which are generated between these two portions, yielding and non-yielding. Now when this slice tries to move down, so this will be the deflected pattern. Okay, so in this way it will try to move. Now when it will try to move in the downward direction, so along the slip line, a slip plane or slip surface, shear resistance will be generated. So shear resistance, the adjoining soil mass, the non-yielding soil mass will try to resist this movement, and this resistance is equal to the shear strength of the soil. Okay, so these are the shear resistance governed along the slip surface. Now what we will do, we'll basically try to consider the force equilibrium of this elemental slice in the vertical direction. Okay, so first let me note down the forces which are basically involved in this mechanism. So first, force V, which is having a magnitude of sigma Vp. Then second, V plus dV, which is having a magnitude of sigma V plus d sigma V times V. Then third, dW, which is having a magnitude of gamma V dz. Then fourth, shear strength C, and this is mu times sigma H times dz, where sigma H is nothing but K times sigma V. Okay, K times sigma V dz. Because you know lateral earth pressure, how you can get the lateral earth pressure? By multiplying the vertical pressure with the earth pressure coefficient. So product of vertical stress and the lateral earth pressure coefficient, so that will give you the sigma H. Now this is the normal stress on this surface. Now if sigma H is the normal stress, so normal stress multiplied by this friction coefficient will give you the shear stress S, and that will basically act in the vertical direction, and this is the thickness dz. Okay, this is the area. So perpendicular to this plane, the presentation slide is basically, the dimension is basically considered as 1. So these are the 4 forces which are basically involved in this mechanism. Now we will consider the vertical force equilibrium for the elemental slice. So if we consider the vertical force equilibrium for the slice, then it will be V plus dV plus 2s equals to V plus W. Now VV will cancel out, so we will only be having dV equals to 2s minus dW. Okay, sorry, dW minus 2s, dW minus, so therefore we can write this dW is gamma V dz, and this S already we have calculated as K mu prime sigma V dz. Now what is this sigma V? Sigma V is nothing but V by V. Okay, so from this equation, from this component 1, we can write sigma B is nothing but V by V. Now if you integrate this equation, so after integration, so I am skipping that part here. So you will get the expression of V as gamma V square 1 minus e to the power minus 2k mu prime z by b divided by 2k mu prime. Okay, so this is the distribution of vertical force with z, where z is basically measured from the ground surface. Now if you need to determine the load on the sphere, so we'll basically consider this z as h, and this value is 8 meter. So if you consider z equals to h equals to 8 meter, so then the calculated V value will give you the load on the sphere pipe. Okay, this rigid pipe. So this value would be, I hope, 67.6 kilonewton per meter, and this is the answer. So we have to just substitute the values there. Okay, so I have skipped that part here. So if you substitute, the gamma value is given as 19, then B is 1 square 1 minus e to the power minus 2 into 0.2 into this is 2k mu multiplied by z by b. Z is your 8 v1 divided by 0.12. So if you calculate this expression, you will get the required V as 67.6 kilonewton per meter. Okay, so this is the answer. So in this problem, we have come to the end of this session. So this is a summary for the entire course, which we have learned from this foundation engineering course, NPTEL course, and these are the references which you can follow for a better understanding of this course. Okay, again, this slide is taken from the lecture materials uploaded in the course portal. And lastly, before ending this session, I would like to extend my sincere gratitude to the course instructor, Professor Kousik Deb from IIT Kharagpur, and my thesis supervisor, Professor Priyank Ghosh from IIT Kanpur, and the NPTEL PMRF support team who has given me this opportunity, and obviously the course participants, means you who have basically actively participated in this discussion to make this session more effective and fruitful. Okay, so all the very best for your end semester examination, and I will end this program here. And still, if you have any doubts or if you need further clarification, you can always utilize the discussion forum, or you can send an email to the what I can say, uh, the reception or the help desk, which is already provided to you. Okay, so thanks a lot and have a nice day. So I will end this session here. So at least for today's session, if you need any further clarification, please uh, you can unmute yourself and tell me. Otherwise, I will assume there are no doubts, or it means absolutely fine from your end, and I will stop the discussion here.